The goal today is to look at an R-theta problem, but from the perspective of how do you use computer algebra to do these kinds of problems. And in particular, what I'm going to be doing is looking at a problem from, first of all, the mechanics of R-theta. What do I need to do to solve for v theta, A theta, the velocity and acceleration, but also, can I use these packages, Mathcad Prime and SMath Desktop, to do these things for me in a better way? And in a better way really means, one, that I do calculations with units, but also at the same time to focus on some of the powers of SMath Desktop personally, which I like, which include calculating derivatives, which I don't have the capability to do with the free version of Mathcad. I have here a problem which consists of a radially slotted arm. It's governed by an equation which is theta equals 0.3t plus 0.03t cubed. Theta is in radians, t is in seconds. Simultaneously, the power screw is in the arm, which is this orange line right here, engages the slider B and controls its distance from O, according to the equation, 0.3t plus 0.045t squared. R is in meters and t is in seconds. And you're asked to find the magnitude of the velocity and acceleration of the slider when t equals 3 seconds. The type of motion you're looking at is this. So the slider is moving from the inside to the outside. First, let's solve it. Let's look at how to go through this. So I've got two equations, r and theta, and I'm going to take derivatives of them. So first one, I've got 0.3 plus 0.04t cubed, and I end up with 3 times 0.04, which is going to be 0.12t squared. Take another derivative for r double dot, 0.24t. On the other side, I have theta equals 0.3t plus 0.03t squared, theta dot, which is when I take the derivative, that one sort of sticks around, unlike the previous equation, and I get 0.3 plus 0.06t. And then for theta double dot, I get 0.06. These are in different units. These are in units of meters, meters per second, and meters per second squared. And these are in units of rads. Rads per second here, rads per second squared. So to calculate my velocity, I've got VR, which is r dot, super, that's my meters per second, I already got that. And v theta, which is theta dot times r, because theta dot is going to be in units of rads per second, and r is in units of meters. So that gives me meters per second as units. So I get v equals 1.27 meters per second if I calculate the magnitude. So v squared, vr squared plus v theta squared square rooted equals 1.27 meters per second. If I do the same thing for the acceleration, I have acceleration, which is r double dot minus r theta dot squared. And you can look at the terms here and sort of do the calculation, but you'll notice that they end up with units of meters per second squared. Same thing with acceleration theta, right there. R theta double dot, meters per second squared. R dot theta dot is meters per second squared. So it ends up with units of 1.2 meters per second squared. And if I calculate the acceleration, I get 1.19 meters per second squared. So I have the acceleration and I have the velocity for this problem. If I calculate this with Mathcad, same thing. I'm just changing my variables because I'm lazy and I don't want to write all the terms out. And so I end up with my constants 0.3, 0.04. Now, one thing you should notice here, in order for me to calculate this with unit consistency, I have to give the constants units. So clearly, for example, b, which is t cubed, in order for it to be a distance, has to be meters per second cubed. Time is 3 seconds. Over here, c, which is rads per second, because the first term is c times t, time, and the second term is d times t squared, so rads per second squared. I can do the calculation in my head. It's not hard to do the derivatives. A plus bt t cubed, derivative r dot is 3bt squared, 6bt when I do rd dot. So I didn't calculate this using math. I did this by calculating directly. So same thing here. When I do theta, I've got ct dt squared, theta dot, which is c plus 2dt, and finally theta d double dot, which is 2d. Again, I'm not calculating this out using Mathcad. I'm doing this in my head. This is not clearly it's not a complex problem here. but it's kind of a pain in the neck because I don't have the option that does exist in the full version of Mathcad. So then I put in all the numbers. I have R dot, R double dot, theta, theta double dot, theta double dot, or theta dot, theta double dot. And you'll notice, of course, I've got all the units. These are calculated with Mathcad. VR is equal to R dot, B theta is R theta dot, and I get both of these answers, which are the same, or what would I expect to get. And I get a final velocity of 1.27 meters per second in terms of magnitude. If I calculate out all of the radial and theta accelerations, I get 0.402 meters per second squared at 1.12 meters per second squared, for a final acceleration magnitude of 1.19 meters per second squared. Again, not a big deal. This is not a complex one. You've done it. You can do this in your head too, but it's a good tool for calculation. But I needed to do a lot of the legwork for this. So let's try and do the same problem in SMath Desktop. So here I have all the same terms, A, B, C, D. I've just called it A1, B1, C1, D1. I've got a problem because occasionally T1, T is kind of a predefined variable. And so I then put in all the terms. I get R1 is equal to 1.38. I can do the calculation where I take the derivative with respect to T1, and I'll get R dot 1. And then I can take the second derivative with respect to T1, and I get R double dot. So if I do this for theta, same thing. I'm doing the calculation over here of theta dot and theta double dot. And I get all the numbers, and they're the same. So there's nothing different in terms of the final result. But the big difference here is that I haven't done any actual work in terms of calculating the derivative. I find that occasionally and inadvertently it's helpful that the calculation be done by computer. I do make mistakes. People make mistakes all the time. This is helpful to sort of correct and make sure you're not making a mistake that you won't catch later. After I do all of this and I sort of calculate the terms, I get the same thing, 1.08, 0.667, 1.27 meters per second. Same thing for acceleration R, acceleration theta, acceleration magnitude. It's not as pretty, but the fact is that I get the same results, and I didn't calculate the derivative, and I didn't pay anything for this because it's a free software. Didn't stress it too much, but really I really have to focus on the definitions. This is the most complex coordinate system because it's easy to forget R dot, R theta dot, all of the terms that you need to calculate VR V theta, AR A theta. This is not it's not the second derivative of theta that gives you A theta. It's that expression that we got in the previous slide. Both of the software packages I've used, I actually use this, and just so you know, to check my answers when I write an exam. So I write an exam, I check my units and make sure that things are correct. And I think you'd find it very useful as you're going over the homework, just to give you sort of that extra bit of confidence in your answers. The other thing is I can't really do it with Wolfram Alpha because I can't download it, and Wolfram Alpha does have sort of an option similar to this, which is Mathematica, but I don't have a license for it, and I'm not planning to just for this. But if you can do Wolfram Alpha on the web, it's extraordinarily powerful and extremely useful. And again, I'll give a shout out to Waterloo and Maple, which I think is a great piece of software. And if there's anything that I think we really should bring to U of T, it is that. Thank you, and we'll talk again.